Yeah. Actually, we can get even those lights off. I think this is like the good talk. You don't need to take notes. You just, should I try this? You can just like watch it like a movie. Yeah, I did all the boring talks. This is the last one you're seeing me. So there are lots of good news in here. Yeah, this is a fun one. So I'm going to talk about little about discovery, and you're about to see how discovery looks like in the NISQ era. This is the work, again, done by, we become capable by the Google infrastructure, and you can see it's done without external collaborators, so it's mainly the Google team that was involved in this work. And if to get some credentials, I can say that just yesterday this got accepted to Nature, so maybe that gives you incentives not to play with your phone. Okay, so after the quantum advantage experiment, one thing happened is that you look at the literature, well, two things happen. First, the language of talking about quantum get very poetic. They talk about dawn of the NISQ era and the horizon of quantum, sun of quantums shining on the ocean of our ignorance. It's very, very poetic language. You can go and read about that. But with every commentary, every interpretation of the experiment you see the word useful, or they say not useful, next to the experiment that we have performed. So the question is, what if we do something interesting, something practical, something useful? So this has been with us since then. It's still with us. So people like to see, there was an article by Andrew Daly and colleagues in Nature recently, practical quantum advantage. So that's the theme of that. Like, how do you get beyond making bit strings and do something practical, something useful? So here is a super rough estimate of where the useful problems are without error correction. So you can make a good, okay-ish qubits, and you can make lots of them, and to make a logical qubit and to make things interesting. That's not the subject of this talk. What we're trying to do is see if we make qubits better and better. Unfortunately, the vertical axis is logarithmic, exponential, however you want to call it, is getting harder and harder. But it doesn't take that many more qubits. You don't need to put that many qubits down, but you need to make qubits orders of magnitude better. Let's say you do that. What kind of problems comes to your horizon? What kind of problems become possible? Spin dynamics, non-equilibrium physics, quench dynamics is the first thing that becomes visible to you. It's things that you can do. It's not surprising. At the end, this is a spin model that we are trying to study, Bose-Hubbard. You can truncate, you can think about spin models. So the bosonic degrees of freedom interacting the bosons, it's become something that you can quickly access. So that's why this is rough thing is drawn in here. And no offense, but condensed matter people are not as good as chemists in doing numerical computations. Chemists are far better than us. They know how to do numerical thing. Maybe it's more ancient, more historic from early 1930 or whenever Dirac said that everything is solved. Now we just have to compute. They start to solve molecules and whatnot, so they are better. But there is this quantum, there is this spin degree of freedom that we have a system that excitation in it bosonic, and you want to do a fermionic problem. So that's why all of a sudden you double number of qubits, and also the ground state problems usually have a structure which makes it easier for the classical computer to compute. So you have to have much better qubits to outperform it. So these things are bubbles are very rough and crude, but still there is some underlying facts that makes them to be here. And so after 3 years and half a dozen articles, you all entitled to question saying that, hey, where is the discovery? Did you find anything? How far did you move? In fact, if I have to put a point associated with these articles in here, they all go down. They all go down in the number of qubits. So threshold of getting to journal is much easier to doing anything practical. But we are not using taxpayers' money, but still we feel obligated to respond to community. That's what we are doing with our time and people's money, I guess. So let me introduce the problem we are going to solve and tell you, maybe it disappoints you of what we can solve currently, but that's what we can do. So is a search for hard problems. Where do you go find hard problems? This is a very again, a rough estimate of where things are. I'm sure the experts in you have known exceptions for every category I wrote in here. That's not the point to hold these exceptions against the poor experimentalists. The point is that you can think, well, as the dimension of the system gets bigger, the problems get harder probably. But then there are problems that can be mapped to free fermions. If they are non-interacting, if your degrees of freedom are non-interacting, they can be written in the quadratic form, and we can call them simple. They don't need exponential resources to be solved. So these are that certain observables are known. Everything is known in principle. So forget about them. And then you come in here, the problems that interacting 1D or 2D, they cannot be mapped to free fermion. No surprise, the cases that we know are not contrived are less. Well, okay, that's the notion of integrability. So we come over here, the problems that cannot be mapped to free fermions. And so that's what most likely interesting problems are. They are not simple. And in this ocean of interacting particles, there are these sets of measure zeros, islands of integrable systems. They're fine-tuned systems that the answers is technically known. So there is analytic solution, there are closed-form solutions. That's what we are going to do. We're going to start with one of them, so we know we have analytic forms. And then we're going to move away from them and say what we are finding. That's the idea, and that's the thinking in here. And such cases exist. For instance, is not so the particular problem that we are going to focus on is the problem of bound states, and I introduced you what bound state is. And a couple of cases is known in the 1D system, and in 2D interacting system, probably obviously is far less is known, and we're not going to get there, but that's probably what is interesting and where we need to be eventually. So let me give you a little maybe historic overview of where, again, difficulty and challenges is coming from in the spirit of this being a school. In 1600s, Newton figured out a two-body problem working under some attractive force with each other, and he solved it. And then about 400 years later, not that we not only could solve the three-body problem, all we could do is just write a theorem saying this is not solvable for the most general cases. The most advanced literature on this is just providing some statistical answers. There's no general closed-form solution, in fact, because of the Poincare-Bendixson theorem. We know it since because the chaos is possible in 3D and not possible in lower dimensions in phase space. So probably is hypersensitive to initial state, so probably is very hard to solve generally. And now we have theorems also showing that this is the case. So sun, moon going around the Earth, we can solve it. But moon and Earth and sun together, we just cannot solve it together. That's how bad we are. And no surprising, all the unsolved problems in electronic models, in Fermi-Hubbard, in finding ground states of chemistry molecule, essentially of that nature, that the interaction between the terms cannot come down to two-body interaction. And in fact, when we can solve them and interacting integrable models, is that the scattering can be reduced to two-body scatterings. So when two objects scatter, their outcome is independent of the third object. And that is exactly the essence of the difficulty here, which we could have known it from the classical models. So that's how the good definition for integrable model. That's where we're going to start. Scattering is factorizable to two in two out scatterings. Essentially, that is sufficient picture. But being an experimentalist, when I see something is solvable and there's this vast unsolvable problem, so definitely I'm going to tune something away and try to illuminate the community, saying that, hey, look, if you go from these non-integrable cases, go from integrable cases, that's something new. That's our plan of action. It's exactly opposite to Achilles, right? He was very much vulnerable from very tiny spot in his body. Here, the whole body is really vulnerable, and we have very tiny islands of stability. Yeah, definitely, whenever you get an experimentalist, they're going to deviate and tell you what they found. This is super obvious. So what is the bound state? What is the spin model we want to work on? Since beta, times of beta, is known that the XXZ Hamiltonian is integrable, meaning that you can use beta ansatz to find the answers, analytic answers for it. And when you know if something is integrable, usually is the matter of time till you find a bound state for it. So it allows the formation of bound states, meaning magnons or excitations that they remain together. I'm going to explain it in more detail. And then it was. I think a team led by Fabian Essler figured out that the existence of wrote analytical form for the bound state. They say, okay, it's an integrable model, so let me find the bound states for you. These are excitations that do not disperse. They look like solitons, but they are very different in underlying physics, but they appear like solitons. And then a team led by Emmanuel Bloch, a year or later, they observe these bound states. So this is the history of bound state in the Hamiltonian XXC model. And then we are at the age of quantum processors and gates, and we don't have Hamiltonian. We have unitary Floquet dynamics. We have unitaries. You can write an effective Hamiltonian, but that's not unique, or sometimes doesn't exist, or sometimes not physical. So forget about Hamiltonian and focus on the unitary. You have a unitary which you periodically apply. It is called the Floquet operation. And to show that XXZ Floquet operation is integrable is the result of the work of Thomas Prosen, who showed that this is integrable. Again, it took few years, and Igor Aliner from our team showed and wrote analytical form for the bound state in the XXZ Floquet model, and then handed to us and say, go and observe it. So here's what we are going to do. We are going to get qubits, put them in the loop. Qubit 24 is next to qubit 1. We are going to have an entity which I call FSIM gates. This is an entangling gate. FSIM gates is parameterized by theta and phi. Theta is the strength of the hopping of a photon between the two sites. And phi is in ZZ terms, is the interaction term between the photons. And we are going to create some initial states, and we are going to apply these gate sequence to them. So one qubit is see a gate with its left qubit, and the next time see it with right, and that constitutes a single cycle, and you're going to repeat this cycle over and over again. And that's there is a cycle, and that's the Floquet. So that's what we are going to do. So what's the big deal? The bound states, like excitons, things that you know from semiconductor physics, they live in the middle of the gap. There is no bulk place for them to decay to. And that's where the usual stability of excitons and whatnot coming from. There's no continuum of energy coincident with them in energy spectrum. So that's why their lifetime is set and their broadening is set, right? How much what they overlap to go to. The bound states are not the case. They exist in the middle of a continuum spectrum, yet down to symmetries and whatnot, they are not decaying to. So in that sense, it's a very unique and is very interesting. And these works of Essler and others show that, well, pictorially, I just told a tight binding thing and a thing in between it. I really don't take it literally. But you see, this is common ones, but then it could really coexist with the bulk continuum, and it still survives. And that's what I will show it to you in our case too. So now we are extending this to the Floquet dynamics. So we have a Floquet, we have eigenstates, eigenvalues of the Floquet are phase numbers on a unit circle, and the continuum of it forms a continuum over the circle, and the bound state coexists with them. And that's the magic of it. That's the significance of it. Here, how the experiment is going to look like. You're going to see the result of this evolution over and over again. You have qubits. You excite a couple of sites next to each other, similar to the case of Magnon that I said. So this is meaning 3 photons. You create 0, 0, 0, 1, 1, 1, 0, 0, 0. You go over for 24 qubits. And then you evolve it, and you ask, where are my photons? The photons, the claim is that they stay together. It doesn't mean, but they get to this superposition state. It doesn't mean you do a measurement, they are always here or there. They are in the superposition of all various spots, but the key is that they are every time you observe it, you read the whole entire chain, they are together. So any measurement would bring one of these superpositions, but the claim is that all these individual bit strings characterized by excitations next to each other. Okay? And let me give you an intuition of why they should stay together and why interaction is important in this case. Or how can interaction leads to formation of the bound state of photons? The way to understand is that the interaction suppresses separation of the photons. Here is a schematic showing that, let's say 2 photons stay together. What are the chances that they end up separate from each other? Let's just think about that. When you think about that scenario, one way to think about that is to consider various Feynman paths that these two can take to get there. Okay, so I'm showing you 3 instances of Feynman paths that they can take. They stay together for a couple of times, and then at the cycles after, they separate. They stay longer and separate. They stay further and separate. So all these scenarios, right? These are the most likely scenarios leading from this initial state they are together to that final state that they are separated. What happens is that this phase accumulation, here is 2 units of phase. Let's say here is 3 units of phase. Here are 4 units of phase. They accumulate phase so long as they are together. And you can imagine this end up to be a random number, which you average it averages to 0. So this scenario, the probability of this scenario is suppressed because the amplitude of the terms that enters the Feynman summation is a complex number that can be anywhere in the complex circle, so they suppress each other. Of course, this is a hand-wavy argument, but the beauty of it is that if you go work out the detail or you read Igor Aleiner's 160-page article, you see exactly that's the outcome of the thing. We good? Okay. Okay, so that's what we're going to do. Put 24 qubits together, close the loop, excite some of them, and then let's see what happens. Okay, start with single excitation. There is nothing to bound to. It's single photon. So it's just going to do its good old random walk. It's just going to diffuse, and it's just going to go hit the edges of the thing and going to interfere with itself. And this is a random walk. There's no notion of bound state for single excitation. And then you put 2 excitation and 3 and 4 starting together, and you ask, are they staying together? And then you get the probabilities. You measure the final bit strings, and every cut here is the average over the bit strings we observe. You write down the bit string you get. You repeat it 10,000 times, and you just add them up. You just add them up of what you're getting, and you see this. So you see. I make it more clear, provide more evidence, but it seems they're staying together for a long time. But sometimes also it seems they break. So you see this single excitation propagation you see, but most of the time they seem to start propagating with a different velocity. And you do it with 3, and you start seeing more concentration of color, indicating that it seems this excitation didn't move forward much. Okay, this is a very hand-wavy, very rough indication that it seems they didn't run away from each other. It seems they're staying together. And the next few minutes, I provide more and more evidence for this case. Let me do the following. Let me just show you the bit strings that we found that they are indeed together. So I have all sorts of bit strings coming out. I'm going to trash the bit strings that the excitations are not next to each other. We're just going to focus on bit strings that excitations are next to each other. And these bit strings can be represented by a single point of it, center of mass of it, right? And here what you are seeing is the position of the center of the mass of two photons. Right, you post-select on the bit strings that they are together and say, where is the center of mass of this object? How is this object moving? And lo and behold, when you're looking at the two, it's very similar to the interference pattern you see for single excitation, meaning these two happily staying together and as if there were a single particle with just a smaller velocity. They propagate slower. And the same physics is going for 3 and 4 and 5. It just got so slow in propagation that the center of mass essentially doesn't leave the origin. Yes?
What's the x-axis again?
Time, cycles. This is a Floquet dynamic, cycles. We good? Okay. So some indication, maybe some of the non-believers of you now converted. I provide more, don't worry. And I can extract the velocity of propagation. I wanted to comment 2 things about it. So you can see it gets slower. This is just this line. The slope of this line is plotted in here. It gets a slower propagating, but also you see that it's ballistic. The edge of this is ballistic, indicating there are not that many particles to scatter from, so it can really propagate ballistically. So meaning that when you this has a good life, and the broken one is really a small portion of the thing. I can also show you how this system is decohering. That's another interesting part. If I had done the numerical simulation, this would have been flat. Let me tell you what this is. This is the ratio of the. Maybe I step back. I didn't say this. The bit strings that come out of it is categorized into 2 categories. T, meaning this category that they stay together, and S, those who chose to divorce, they are separated, okay? Technically, in the definition, NT over NT plus NS should be a flat number, should not decay. But I'm showing you this post-selection and whatnot that I was telling you is focusing on what fraction of them. Numerically, this line would have been flat. Experimentally, they are not. And they are indicative of the fact that due to decoherence in our system, there is some, it leads to breaking of the bound states. That's what it says. But what's also interesting is that is a linear scale on vertical. The slopes are very close to each other, meaning that the 2 photon breaks as frequently as a 5 photon case, meaning that the breaking happens, the coherence, the breaking happens from the edges only, and the center ones are kind of protected or somehow, meaning that there is a little protection is provided, the suppression of the decoherence as a result of forming these bound states. Nevertheless, they decay, and they're not going to stay together in contrast to what theory predicts to you. But that's the ratio they decay, that's how fast they decay. Good. Okay. You see? Meant to be replaced, but when they don't respond to my emails, that's what happens. So I want to show you what fraction of things remain together more systematically as we study them. Yeah, they're fantastic. So at cycle 0, we prepare 2 initial states. One is the S-bit string, and one is T-bit string. And we look at the dynamic of them. You see, at time equals to 0, these are top ones for various number of photons. We put, and this is how far the shape of the bit string. Initially, let's say the blue histogram is that at time equals to 0, we only made this type of bit strings, and we look at the future bit strings we find. The horizontal axis is the number of vacancies, is the number of holes, the number of lack of photons that enter a bit string, right? Here, for instance, 2 vacancies, to unoccupied site enter this. And you can count how many holes you're getting inside your bound states. what is right? T is there's one type of T. They're all together. S could come with one hole, two hole, or whatever number of holes in between them. And here is the histogram of what happens in time for 2, 3, 4, 5 photons. You can see blue, meaning that they stay together. They start together and they stay together. That's the claim we are trying to make in here. They start together, and for a very long time, they stay together. However, if they are not staying together, they explore the most part of the available computational state. And these numbers, which I'm owing to you and I don't have it, is trying to show you that the fraction of the Hilbert space that they get stuck to is tiny, exponentially smaller, than the available space they can go into. This is showing if they were just going everywhere with the equal probability where they end up going to. That's the gray line. And you can see the size of it, the number of configuration that they can stay together for a chain of n qubit is n. The number of configuration that you can go get some holes in between is exponentially more. And you can see that there's absolutely no gray line visible in here and much more visible in here. So the beauty or the challenge or that photons have to accept is to stay in this very tiny part of the Hilbert space. They stay in a corner of the Hilbert space which is exponentially small, and that is challenging. But again, it's further evidence that they stay together. Okay, so this is condensed matter place, and I want to show you band structure for real. But before I do that, I want to tell a little about physics of how we measure band structures. Because we are trying to show that these photons, indeed, they form their own band, and you can talk about effective mass and effective charge. This is important, and we want to look at the response of the band to the magnetic field. But first, we need to invent a spectroscopy technique to be able to measure the momentum of the particles and their K, E versus K, essentially. Okay, I'm going to tell some trivial physics, but soon we're going to turn this trivial physics to something that allows you to do the spectroscopy I'm mentioning. So you have a Hamiltonian and eigenstates of the Hamiltonian, and if you evolve the Hamiltonian, evolve the initial state with the Hamiltonian, you get a bunch of prefactors and phases and whatnot. But if you somehow could manage to make the overlap of the final state with the the evolving state or the final state with the initial state, you get something like this. You get a complex signal which has lots of oscillatory terms, but the magnitude of them tells you which eigenstates you had initially, and the oscillation frequency of them tells you the energies of the system. Okay, I'm not doing anything magic. I'm just connecting two impossible things or very plausible things. This is Hamiltonian evolution, and I'm just saying, suppose you could measure that. Good luck measuring that. Measure overlap of initial state with a psi t. That is exactly what you want. If you Fourier transform that, one could hand to you, would have peaks at the eigenenergies of the system. So it's very good to try to get that. How do we get that? Well, by getting clever or hiring someone who is clever. That's what we did. So you put one qubit in equator. Let me show you the single particle physics, and then we extrapolate to many particle physics. You put one qubit in equator, you evolve it under this Hamiltonian U, which is particle conserving. So your initial state you created is 0, 0, 0, 0 plus 0, 1, 0, 0. And you evolve it under Hamiltonian U, and you measure non-Hermitian operator, okay? I don't know what they teach you in school these days, but we can measure non-Hermitian operators. This is a myth that you cannot measure them. You just measure different things, and you just add them with complex prefactor. You measure expectation value of X on qubit 2. You measure expectation value of Y on qubit 2, and you just add them up. These are two independent measurements, and you construct measurement of these lowering operator. if you go through the math, which is in the supplement of this paper or the recently accepted paper, you would see that this expectation value of this guy is exactly that thing that I write with wishful thinking. The psi naught psi t is exactly expectation value of this, given this initial condition, is exactly that. So, so it takes two steps. One is to be clever with initial state. There are lots of ways to get that wrong, and you got to get clever on what you want to measure, and it has to be photon conserving. You get these three together, you're doing a spectroscopy. Then we did a Hofstadter butterfly with 9 qubits with this technique because the non-interacting electron in 2D can be mapped to 1D case, so we could do that. So, okay, let's keep going. You put 2 qubits on equator, and then you make this initial state, and you're going to measure this observable. Now it's getting lowering operator in 2 qubits. So it has 4 terms, and terms that you couldn't care less. And measurement of this observable would give you exactly the spectrum that you want, get the overlap you want. The method is not scalable, so you cannot go infinitely large with this. But we pushed it and pushed it as far as we could do. But yeah, I think it's powerful. But also, this is not the cleanest way of doing it. The one who was on the driver's seat got a little lazy. You have to do CZ and make a proper initial state. This is a bit. This initial state has many undesired terms. You should not create these terms in here, but that was a lazy solution in case you know there are better ways to do it. Indeed, there are better ways to do it. Okay, so that's the Hofstadter butterfly single excitation coming from just doing that. Okay, so when you do this in the lab, what do you get? Absolutely nonsense. You just get to go space and time, and you measure these 4 particle, these local observables. You keep adding them up, and you get, yeah, look like nothing. But when you do the Fourier transform, that's where the fun happens. You get a beautiful cosine-looking band structure. This is the Fourier transform of this mumbo jumbo. That's the power of it. So it's amazing. You just get 4 correlation things. You just add them up. We are showing 2 of them in here. You add these things up, and then you Fourier transform of what I just showing you. You construct this object, you Fourier transform it, and you get the band structure. Okay, right? Space goes to momentum, and time goes to energy. Okay, of course, we're going to add the person to continue. And we have been able to push it all the way to 5 excitations, meaning that you have to add 32 Pauli terms. Each of them is 5 Pauli string long. You have to get 32 things. Some of them can be done simultaneously, but again, it's not scalable. But scalable is not as bad as you might think. You just do it. You get something which is very disappointing. You Fourier transform, you see the band structure. The bands are getting flat, indicating that the interaction getting stronger, but nevertheless, you can see signatures of that. And then there is analytical result from Igor Aliner that tells you that these are not exactly cosine. E of k is not cosine of k. E of k is cosine inverse of cosine of k or something. But I don't know. Anyways, you can see fits and all that is all coming together nicely. And now you're in business. You can do fun things with it. For instance, you can check some of the Igor's predictions for the very first time. For instance, one of the prediction is that you would see bound states in a certain regime of FSIM angles, a certain regime of hopping and interaction. If you go below that, you would not see that. So when you're strongly interacting, phi is bigger than 2 theta, you would see it. However, when phi is not bigger than 2 theta, you're not seeing it. Nevertheless, you see it at 2 tiny points over there. And this hand-wavy Feynman argument that I offered is actually enables you to explain this too. So it's interesting. Let's go over it. Essentially, in these very special K points, you evolve it, and then you think, okay, what it takes to break? What if I have this bit string? What if it breaks? When it breaks into these two possible scenarios. What if this one breaks? It would break into these possible scenarios. But then you can package them differently, and they are two different parts of the Brillouin zone that the prefactor of them exactly cancel each other. And you can see everything I put in the box, one is come with e to the, I think there would be exact cancellation at these points. And so all these scenarios are suppressed. So the breaking of the photon bound state suppresses. Therefore, they stay together for these various special points. And anything else, they are evaporated. Okay, enough of testing on Igor. Let's move these bands in a magnetic field. And that's a cool thing to do because it tells you about the effective charge of the band, right? We want to see these, essentially, they are forming a quasi-particles. They are forming these quasi-particles, forming a band. Now we want to see what is the effective charge of these particles. So we are going to get a magnetic field going through the system and measure that how fast the bands move as we change the flux penetrating it. How are we going to do the flux penetration? It's super trivial. There is this gate. It's so trivial that we even didn't write it. There is a single qubit rotation before and after of each in each entangling gate. And honest to God, I don't know if we have done it or we have done it virtually. And the contrast is phenomenal. Okay. Yeah, it's a single qubit gates, which gives you the complex hopping, and the summation of this complex hopping is gauge invariant because the loop is closed, and when you add them up, essentially you have a flux that goes through this loop, and look how this band moves as we change the magnetic field in it. So we can repeat this. So we can extract an effective charge in here, see how it moves as a function of flux, and long behold, the charge extracted by this method is 1. Igor's prediction was 1. That's good. And you repeat the experiment for 2 and whatnot. And this is, I'm not sure if you see or not, I complained about changing the contrast on this. It's when you get to 5 excitation and you move the flux in it, and you see how fast the bands are moving in K space. Don't ever think this was simple. This took about this case was simple. This took about 100 hours to arrive at it. So let me fully disclose the data. Well, this panel, I think, took about 100 hours. And again, look garbage. So to be sure the lead experimentalist is not putting the dots wherever he likes. We say, well, you got to convolve these together and look for the peak. You just cannot put the point wherever you feel like it. So you convolve this with the later instances to see how much shift is needed to capture that. For small number of photons, beautiful. For 5, the data we are showing is the peak in the convolution, right? You auto-convolve and say, where is the maximum overlap? And you call that the effective mass, effective charge. We good? Yes? There is a physical gate. Maybe in the paper we wrote it. So, you see, are you happy with this action? There are qubits, and every time the qubit experiences this entangling gate, right? Imagine there is a tiny box before and after each gate, which is a single qubit rotation, and that is doing the synthetic field. So there is actually 30 nanoseconds of someone doing something.
Yeah, but no Teslas, right, to put it in physical terms?
Sorry, what?
There's not a physical magnet in there, I suppose, right?
Oh, no, there's no physical magnet. Well, and there are photons. Why you even need a physical magnet?
No, from your drawing with the flux sign, I kind of interpreted like there was an actual flux penetrating your transponds.
It can be, it's a synthetic flux. It's a synthetic flux for, all you need is that your photon, upon hopping, collect a complex phase. And we managed to do that.
With a single qubit operation.
With a single qubit operation. And it's gauge invariant because the loop is closed.
But you drive it electrically, I suppose, right? You address your qubits electrically?
Don't worry about that. There is a 2-qubit operation, which, if forget about this phi, huh? The center part says that, you know what? Actually, I brought it in here too. This is actually, maybe that's why I'm repeating it here. Beta, we realize this.
Okay.
Okay. No. It's a. So that you need to accumulate a phase upon hopping, and this is achieved by rotating the qubits between the gates. There was a hopping term, and now I rotate this qubit after the gates every time I something like that. Super trivial. There are advantages to this platform, I tell you. Okay. Okay, now the discovery part. Now the part that we are going to tease Igor and Lev on their thing. So now we have resolved the quasi-particle bands structure, and we can see that the photon excitation and the 3-photon band, the 3-photon band is really in the middle of the continuum of the band. So that part, this schematic has been drawn based on the band structure that we painfully measured ourselves. You expect that if we do something crazy like this, we are going to break the bound states. And they say, you're going to break the bound states, and let's break them and see. We want to show that you break the integrability. Remember the Achilles heel? You break the integrability, and then you expect the bound states go away, right? That's the condensed. If I didn't forget and go and hand a paper to condensed matter theorists or whatever, say that, hey, draw what would happen, they would say, oh, immediately, as soon as you introduce this perturbation, the bound state is going to go away because they are coming as a result of integrability. So what's happening in here, we have a chain of 14 qubits, and we added 7 extra qubits to them. So by doing that, we are focusing on the 3 excitation case. So we are increasing the size of the Hilbert space by factor of 3.6. And, well, the physics is captured in the Fermi golden rule, but the naive usage of it is that you have certain density of states at the place that your bound states are, and then the matter of overlap of them sets how fast and how quickly you are going to lose your bound states.
Oh, sorry. I mean, isn't it there's this paper, avoided quasi-particle decay, so, I mean, isn't if you have, interaction, if you couple, this bound state to, the continuum, and there's, place to go, then they show that, you should expect it to, not decay, because it's kind of, pushed below the continuum. Do you know what
No, I don't know about that, but the idea is we are right in the middle of continuum, and you expect that this bound state is going to quickly evaporate, and we are about to see what happens.
Yeah, I mean, I don't know, there's this Versen, Mössner, and Pollmann paper, I think, where they kind of show, that the expectation should be, the opposite, but I don't know, not sure whether it applies here. Maybe someone, probably, you know.
I know what you're talking about, but that applies if you have a continuum that you're bringing towards your state. So that paper, your expectation will not be inside the continuum.
Oh, okay.
Bring down the continuum, and it repels the expectation. But here,
We are in the middle of the wilderness of continuum.
Okay, thanks.
We are not at the mercy of gaps. Okay, so let me show you what this ratio I was showing you, the coherence thing, that, hey, this is how I use the bound states when I have this theta prime angle equals to 0. So the strength of the coupling to these extra qubits is parameterized by theta prime. The swap, the hopping to these extra qubits, is parameterized by theta prime. And we are going to change this theta prime from 0, which means nothing, to fully perturbative case. So if you don't do theta prime, set it to 0, you get this line. And then if you make theta prime equals to pi over 2, you get this very hard to see line of yellow. But essentially, this is the expected behavior of just, bound states evaporating. But what is interesting happening is theta prime, the strength of our perturbation, is at the size of the dynamic within the chain itself. This is not a joke. This is a really serious perturbation. But the line we are getting is really up there rather than this dashed line draw with hand, expectation of that it drops there. So it really stays there. Let me show you more data. So we really slowly move it, and you see the bound state, we really show strong resilience toward breaking. Okay, that's something. Let me show you data differently. This is a cut in here. This is this plotting of the same data. This is a cut at this cycle 40. So you see in up to the swap angles theta prime, in the order of the dynamic in the thing, there's a much bigger perturbation that perturbation should be valid. The bound state is actually stays put together, so this more or less is flat, and the curvature of it is also not in the direction that you like. You would have predicted naively, and then it goes down. So this is the real space evidence that the bound states stay put for a much longer time. What happened? Oh, well, you might wonder that this perturbation we did was not clever, and it really did not break integrability. So we asked Dima Abanin to do some level of statistic to show that indeed you're breaking the integrability. These are numerical work, and to really characterize ergodicity or being sure that you're really getting to these extra levels you created is just to look at the level of statistics. And you can see that indeed you're getting to the COE, circular, why should I even try to say that? Circular or orthogonal ensemble? No, something, yeah. Oh, it is? I know CUE, I forgot COE. Okay. This is for huh? You have it written. for a reason. So you can see when you when you go to this strong perturbation I'm talking about, you really get to COE, and there's no indication of so the levels are really repulsing each other very strongly. So the whole Hilbert space is indeed available, and integrability is indeed broken. Nevertheless, when you look at the momentum state picture that, I told you the torture we have done ourselves to get the momentum picture, you see the same picture. So this is the peak associated with the bound state at zero perturbation, and this peak dissolves slowly. But when you look at the full width half maximum of it, you see that indeed it stays together for a long time and then goes off slowly. While if I didn't forget to ask a theorist to draw a line based on Fermi golden rule, that's what they would have done, basically. That's what, but you would think that immediately as soon as they start the perturbation, it takes off. So it's a bit of mystery, it's a bit of puzzle, but that is the point of this platform. The whole experiment, of course, could have been done in your laptop in one evening. But what we are saying is that this is another way of studying novel physics. And of course, if we had done it in 40 and 50 qubits, it would be outside the reach of computational realm of classical computation. But what we are saying is that, this is another method of discovering new physics. So the scenarios that come to mind to explain it, we just didn't throw our hands up in the air and say we cannot solve it, was mainly based on hidden conserved quantities, meaning that which we show is not the case by going to the level of statistics. Then there's also of incommensurate energies and pre-thermalization and whatnot, but all those arguments, again, coming from very small perturbation, and if that is applicable, now we are suggesting that these can be extended to a strong perturbation. And emerging symmetries, or there's some symmetry emerge as a result of what we do. I don't know, but it seems to me a bit of tautology, like you're just not providing explanation, but you're just using a different phrase to say that it didn't break. So we don't know what's the explanation. All we know is that we can say is that this term, this overlap of that enters the Fermi golden rule is much, much smaller than what a naive estimate would suggest. Okay, we have some numerical confirmation that what we are seeing is more or less stable to strong perturbations, yeah. So this is we can do for go very large system sizes and whatnot for certain cases. So it confirms that's finding. So now we are guiding where to numerics to go. So of course numeric can outperform us, but we are after fact. Then numerics could confirm what we have done. Yes.
Hi, I wanted to ask if you were looking at a Hamiltonian system, what is the phase that you will be?
Oh, sorry. Yeah, during this talk, I really move back and forth between Hamiltonian and unitary. So are you talking about the golden rule that I wrote?
No, if you were, say, if I was doing exactly the same dynamics, but with a Hamiltonian system, and I have to choose parameters, in which regime I would be? So I would be in a regime that, so you have the XSC chain, and are you doing, say, could I think that I have an initial state that is close to the ground state? I can think that it has low energy. Like, is there a place you would place it?
Yeah. I don't know top of my head if I translate, but these are very strong interacting regimes. Maybe close to the Heisenberg. The prefactor of ZZ is close to XY, I think. I think actually the work of them is on Heisenberg. Yeah. So we are also close to that. If you really insist on hearing a Hamiltonian, but there's no Hamiltonian. Hamiltonian would have long range and many terms and whatnot. There's only a unitary in here.
But if I were doing the same with a Hamiltonian and the same type of
Heisenberg.
Yeah.
The prefactor are all the same. But and then the perturbation is as strong as this.
Would I observe the same thing in the numerics? Or?
I don't know. I don't know. Someone has to go pay them to do that. Okay, what's the take-home message for you in a higher level? This FSIM gate is a very powerful thing that we have come up with, or we have get a hold of. And in the supplementary of the work, we show that you can change theta and phi on demand, and you can go any regime of that you like with a high fidelity. So these are the angles that we hit for this work. This is some calibration idea. And here is the histogram of the errors that we achieved by doing that. And the point of showing it is that we are really in control of these errors, and we know how good they are, and we can really get these errors down to about 1% in most of the cases. And showing this 2-qubit unitary and telling you that I can put theta, beta, and phi, anything you like, should really inspire you to think about vast majority of the problems to do in this. My personal reward in this project was actually seeing Lev going through a phase transition. It was very rewarding moment, and we have to work harder to get Igor to go to any transition. Okay, thank you.
Very much.
Sure.
Now there is still a little bit more time for questions. So are there any questions or comments? Yes.
She finished on time.
I was wondering, so the pictures you presented looks like you change the chip every time for the specific problem you want to consider, right?
No.
No?
No, they're all the same.
Yeah, right.
Nominally.
But it's a circle thing compared to this NISC stuff that you've done with
No. You just choose your qubits and turn the couplers. You have a grid at your disposal, maybe 70 qubits or so, and you can just draw a line and say, oh, these are the qubits I want.
Okay.
In fact, I tell you a secret. That's why the 1D data is always cleaner, because they have lots of options of which qubits to choose.
And what do you do with the rest of the qubits then? You just use them
You passivate them. You turn them off.
Okay. Yeah.
They're there, but you don't. Every qubit is decoupled from everything else. So unless you turn on the coupling.
Okay. Yeah. Okay. I see. Thank you.
Maybe a question to that. So when you have, let's say, a 1D that you have many paths to choose, then are you doing statistics?
Yeah, we do. You do. Yeah. Yeah.
and see then the difference between the different paths, etc. So
Yeah, usually people get lazy and they just pick up the best and they just go for the, yeah. But the system is calibrated every day, so every day you can look for the best set to choose from and all that, yeah. But I can assure you these are typical measurements. If we do cherry picking, I would be telling you that we have done cherry picking and showing the best, and it's not typical behavior. But getting 1% data on gates is very typical of the system, so it's not a cherry picked case.
Yes, sorry, one more question. Is there possible to do actually a scattering of bound states with this? Say I prepare some initial bound state and I give some kick and I have 2 bound states and I can look at the how the energy of
Yeah,
this state
so
appears.
something, well, if it's not at, yeah, I think actually we need you, because I keep asking, when you, with the problem is this, yeah, that's a good point. No, the answer is we didn't do it, but the thing is here, right, that when you do these initial states, you just make few in the middle with k0. It's a superposition of many, well, it's superposition of many k's, essentially. And so if you can come up with an effective procedure to give a given k to a couple of them, a very compact sequence of gates, then we are in business. I really like to see that we didn't do this, because no one, yeah, people got lazy and they just say, oh, look, these are enough evidence. But I really want to smash them, but someone have to tell me how to make the wave packet. It's just an ugly problem of defining how to write a wave packet. No one was willing to do.
Thanks.
Yeah. Sure.